Hello, good morning, everyone who is present. I thought I usually disable that waiting room for this thing. Today it was not like that, is it? Anirudhan and Adityan, you came.
Yes, there was a waiting room.
There was, but usually I disable that because for that.
No, I didn't get into a waiting room though.
Oh, because I usually disable that so that one didn't have to take permission before entering. So today when I saw it's one more person. I don't know. Probably I had forgotten to disable that.
So now you can just go to security and the bottom of your screen you'll see a security tab.
Security bottom.
On the bottom near participants you'll see a security, and there you can disable waiting.
Oh, yeah. Okay. Thanks a lot. Since I am not, I'm still quite unused to this kind of technology. Many things are rather okay. Anyway, so now any person who comes now will not have any problem, right? Right? He can enter without getting the.
They can directly enter. Thomas just entered.
Yeah. Thomas, I just remember I put admit, but for example, Aranya Bhaumik has been a regular person. So, okay, thanks a lot. I'll share screen soon. Yeah, so today we will begin with stationary probability distribution. This is not part of the midterm syllabus, but then we have to proceed. So let Xn be a Markov chain and state space is a countable set S and transition probability matrix P. So straight away we go to the definition. Let pi be a probability distribution on the set S. So that means, let's say we denote by pi sub I varying over S, such that each pi sub I is greater than or equal to 0, and summation of all these pi I varying over S is 1. And so these two things just mean that pi is a probability distribution on S. And the defining equation for stationary probability distribution is summation over I, pi I Pij is pi j for any j in the state space S. Okay. So please note it down if you want to. This is an important definition. Stationary probability distribution, we will be looking at quite a bit. So if these things happen, then this pi is called a stationary probability distribution or a stationary probability measure. Sometimes these are also, such an object is also called an invariant probability distribution. The reason for using this adjective, stationary or invariant, will come soon. Like the intuitive reason. That is not really intuitive, the mathematical reason.
Sir, have you started the lecture just now?
Yes, I was just mentioning you.
So can you go to the first slide?
This is the first slide.
It is the first slide.
First
Okay.
slide shown in 3 parts. You are seeing the whole thing now.
Okay, so it is the first slide today, right? Right.
Yes, you can.
Okay. Just wait for a minute. Just.
Sure. Somebody's mic audio, this thing is on, please. So
Sir, I just had a question. So what does the last summation signify? Means sigma pi I Pij.
That is the defining property for stationarity.
Okay.
You will see many of these things, the meanings.
Okay. So basically, sigma must be sum of all the values of pi must be 1. That is one condition.
Yeah, that these two conditions mean that pi is a probability distribution on S.
On S. Yeah.
So this
And
is the defining property for stationarity. One
These
could
are
as well
different-
have started with let pi be a probability distribution on S.
okay.
And if it satisfies this, then this is called a stationary probability.
Okay. So these dimensions stationary. Okay. Okay, fine.
This is the defining condition. That is why this has been sort of written separately like this.
Okay. So here Pij is the transition probability matrix entries, right?
Yes. See what is mentioned here.
Okay. Okay, sir. You can go to the next slide.
Okay. Followed by another definition.
Can you just once again go to the previous? Okay, sir. It's fine, sir. Fine.
Suppose pi is a stationary probability distribution for the Markov chain Xn. In addition, suppose one has limit n going to infinity of p super n ij. That is, you take this transition probability matrix P and take its nth power. So this is the n step transition probability. So note that P super n sub ij is the probability of reaching j after n steps if one starts from I. So as limit n going to infinity of this is pi j for every j. Now here note that in this case, this P n I j depends on n I and j. And since you are taking limit over n, one would expect that this would depend on I and j. But there is no dependence on I. In other words, in this limit, from where this Markov chain originated is basically forgotten. Okay. So if this happens, then this stationary probability distribution pi is called the limiting probability distribution for the Markov chain X. Sometimes this pi is also called steady state probability distribution. So we will generally use the word limiting in this case, and the earlier case, we will generally use the adjective stationary. But in some books, if you come across invariant or steady state and things like that, it is so that this doesn't impair your proceeding with that. So these two definitions are quite important. Much of this subject is geared towards looking at these objects. You remember when we talked about generalities initially, one of the primary concerns is to sort of understand the limiting behavior. Please take it down. Okay, before we go to the next slide, I want to point out something. Note that in this defining property, the Markov chain Xn doesn't explicitly enter the picture. Nor does it enter here. The Markov chain Xn does not explicitly enter the defining property. So these things, the dependence is only through this matrix P, which is a stochastic matrix, as you know. So note that that's what I had mentioned just now. In the defining requirements, the Markov process Xn does not enter explicitly, but only through the transition probability matrix, which is a stochastic matrix P. So sometimes that pi in the first definition is also referred to as a stationary probability distribution corresponding to the stochastic matrix P. And similarly, the second definition, pi can be referred to as a limiting probability distribution for the matrix, stochastic matrix P. Please note it. All right. So this exercise, the first part is, if pi is a stationary probability distribution for Xn, then one can show that summation over I, pi I, P super n ij is pi j for all j. In other words, it is, if it is a probability, stationary probability distribution for the stochastic matrix, it is also a stationary probability distribution for the stochastic matrix P power n. That's the meaning of this. The second part, this sort of explains the word adjective stationary. So if pi is a stationary probability distribution for the Markov chain, and if the initial distribution itself is pi, that is, the random variable x0 is distributed as pi, then one can show that Xn is distributed as pi for all n equal to 1, 2, etc. So if the initial distribution is pi, then each Xn also has the same distribution, so that the initial distribution doesn't change. That explains why that adjective stationary, that it is not moving. The process is moving, but that distribution doesn't change. And the same way, that invariant probability distribution, that also has same meaning.
So this means that if pi is a row vector, then pi times p is equal to pi, right?
Yes, very, very, very good. This equation, as he has pointed out, in terms of the matrix language, if you regard this guy as a row vector, and this is a matrix, let us say we are in the n finite case, n cross n matrix, this will be a 1 cross n. Pi would be a 1 cross n matrix, and So therefore, pi multiplied by p, matrix multiplication, is again pi. Yes, very good observation. Now that one has observed it, can you say something more on that, assuming that P is a n cross n matrix? Any of you? From what you know from linear algebra? Probably you write it in terms of the matrix language as he has suggested. Pi P equal to pi. Okay. I will sort of make it, maybe I should not give the answer, but otherwise I'm also this thing that you maybe keep thinking about it and they may not pay much attention. See, that would mean if you interpret this as pi multiplied with p is pi, that means this pi is a left eigenvector of p corresponding to the eigenvalue 1. Okay, we will see this later. Just keep this in mind. Good. I want people to anticipate certain things like this. Very good. Who was that? Kapil?
Yes.
Oh, yeah, good. Yeah. Okay, let's go to the, so this sort of explains the terminology, the reason for stationary probability distribution, calling it stationary probability distribution. Now let us look at a theorem. Let pi be a limiting distribution for the Markov chain Xn. So what this means is pi is a stationary probability distribution, and in addition to that, it satisfies this property. That is the meaning of saying pi is a limiting distribution for the Markov chain Xn. Then the following hold. First assertion, whatever may be the initial distribution of Xn, limit n going to infinity, probability Xn equal to y is pi sub y for every y. In terms of that limiting definition, this is to be expected. But of course, since we are making that assertion, it needs the proof. It's intuitive, to be expected. As a matter of fact, it would have been a surprise if had this not been true. And another thing is that if pi is a limiting distribution, then pi is the unique stationary probability distribution for X. Say any limiting distribution is a stationary probability distribution by definition. So this asserts the uniqueness in a bigger class. Please note it. Okay, first let us prove the first statement. Let the initial distribution be nu. So x0 is distributed according to the measure or the probability distribution nu on S. Then probability of xn equal to y. So conditioning that event with the initial point being x0 equal to x, then it is this. Summation over little x varying over the state space. Probability, conditional probability xn equal to y given x0 equal to little x, and then multiplied with the probability of x0 equal to little x, which is precisely nu x. Which we will write as nu x multiplied with p super n xy, so that you know that the summation over the repeated index x. Now, as pi is the limiting distribution, limit n going to infinity, p super n xy. So this guy, as n goes to infinity, that goes to pi sub y for all x, independent of x. Please note it down. Okay, I will go to the next slide. Therefore, continuing from here, limit n going to infinity, probability xn equal to y. Of course, we have seen that probability xn equal to y is this sum. So limit of this. Now, if one can bring the limit inside, that is, if this step is legal, then we will have summation over x, nu sub x, limit n going to infinity, p super n xy. But we know that the limit n going to infinity, p super n xy is pi sub y. It doesn't depend on x. So since this summation, I mean, this doesn't depend on this, y is not occurring in the summation, take that out of the summation. So what you have is pi sub y summation nu x, x varying over s. And we know this summation is equal to 1 because nu is a probability distribution on s. Please note it down. So in other words, this proves the first part of the theorem. Remember, the first part is, yeah, this. So this proves the first part of the theorem modulo justifying this step. Okay, in the next slide, I will tell the reason why this is legitimate. Those of you who are not able to appreciate that, just take it for granted that this interchange is okay. We are not committing any sin here, that is mathematical sin, by interchanging the limit and summation. Okay. So in the above, interchange of limit and summation is justified by using dominated convergence theorem of measure theory. Note that all these P super n xy's are probability of some event. So they are all dominated by 1. And the constant function 1 is an integrable, say integration with respect to the probability measure nu is nothing but summation. The summation over x is nothing but integration over that measure nu sub x. Under these conditions, the dominated convergence theorem of measure theory allows you such an interchange. Anirudhan, the dominated theorem must have been proved, right? In your measure
Yes, sir,
theory?
he did it in BV Rao did it in.
Yeah. I think he must have gone much ahead of such things now. These should have been in one of the initial things.
Yeah, he is now doing strong law of large numbers.
Oh, strong law
And
he has come, is it? Oh.
And Kolmogorov's series, 1 series, 2 series, and 3 series.
So none central limit theorem?
Central limit theorem he isn't touched yet.
Not okay. So that will be one. See, strong law again we will be using in our course later. So he must have done integration theory first, right?
Yes, he started as measure theory and then went to some integration.
No. What I mean to say is construction of Lebesgue measure.
Yes, he did that.
That usually I thought he does the integration theory and then does the construction of Lebesgue measure.
Oh, he started with construction, Kara theory and all.
Oh, yeah. Okay, very good. That is the logical order. But sometimes, from the point of view of teaching and so on, the integration is done first for abstract measures, abstract sigma finite measures and things like that, and then comes to construction of Lebesgue measure, because construction of Lebesgue measure is rather intricate. I think you would have seen.
Right.
I mean, and why exactly one needs sigma algebra, etc. That comes through there. Yeah, good. So this is a kind of trivial application of dominator theorem. You would have seen in the Professor Bivra's course much more intricate usage of DCT. Actually, for those of you who may not be doing measure theory, the dominated convergence theorem sort of gives us license to many things which we have been doing in analysis regarding interchanging summation and integration. Dominated convergence theorem and monotone convergence theorem of measure theory that gives you kind of permission to do these things. Yeah, if he has come to strong law. Strong law is again a very intricate thing. The statement itself is, it involves a very strong notion of convergence. Yeah, good. I have not talked to him for a couple of weeks. Maybe I'll do it. Yeah, those of you who are doing measure theory can go back to your some of the things you have done in analysis, various analysis courses or calculus, where the interchange of the limit and integration, those things you can try to justify, give the proper rigorous justification in terms of DCT or MCT.
So, sir, what is DCT MCT?
Dominated convergence theorem, monotone convergence.
Okay.
So
Okay.
if you are not doing measure theory, don't bother. Measure theory is quite a technical subject. So you just assume that all these kind of steps have been legalized by measure theory. Okay. Sometimes some problems arise when people, without realizing that or not having the proper intuition, at least they interchange and get into trouble. Okay. Anyway. In other words, to make these things rigorous, these are necessary technicalities one will have to go through if one is pursuing a mathematically rigorous discipline. Okay, I think I'm more or less through. So now second part concerns uniqueness. Suppose pi hat is another stationary probability distribution for xn.
Sir, can you go to the previous slide? The one before it? Okay. Just wait a minute, sir.
Please note down.
Okay, sir, it's fine. You can go on. Go on.
For those of you who are not doing measure theory, but this kind of things, you can take it as a kind of motivation to study measure theory. This kind of arguments. But measure theory is a technical subject. So if first measure theory is done and all these things are going to be done later, I think people may just run away. That is why measure theory is usually introduced at a senior undergraduate level or in a graduate level courses. The logical way of doing things and the pedagogical way of doing things can at times be different. Sometimes the pedagogical way may be exactly the reverse process. And the subject has developed like that. All the major theorems in integration were invented or discovered long before measure theory was available, about maybe 100 years earlier than that. All the famous the theorems due to Newton, Lagrange, all these fellows, including Stokes' theorem in multidimensional calculus, Green's theorem, many things. Some of these things you might have done in your calculus course and so on. Okay. So suppose pi hat is another stationary probability distribution for xn. Suppose the initial distribution is pi hat, that is x0 is distributed according to pi hat. Then the first part B of the exercise, says that if pi is a stationary distribution and excuse me, if the initial distribution itself is pi, then the distribution of xn is also pi for every n. So by part 1, we now get this. We have seen that since it is pi is a limiting distribution, this is equal to that thing. See, since here it is independent of y, therefore pi hat y is also limit n going to infinity of p x and y. So use that, then you get this. There is one more step you have to write here. I leave it to you. Because of this, next step can be pi hat y is limit n going to infinity of p x and y. So this completes the proof of the theorem. I will stop here for the day. I want to do 2 examples. One, an example where the limiting distribution, the stationary probability distribution is also the limiting distribution. And another example where the stationary probability distribution is not a limiting distribution. So those things I want to do at one go. So that we will take up next class. So please note it down, and if you have no further questions and things like that, we will stop sharing. Okay. So take care, all of you, and we will meet again on Monday.
Okay, sir. Have a nice weekend.
Thanks a lot. Thank all of you.